So the problems are 1, 3, 5, and 6. Okay, for from the solved problems. And the previous problem that we have done in the class, uh, for the same problem, you try to find out what is the specific thrust I in case if we use a convergent divergent nozzle. Okay, so in case if we use a convergent divergent nozzle, this outlet, so only the last part will vary. The outlet pressure will be equal to ambient pressure, and the expansion will occur up to the ambient pressure. Okay, so you have to find out. So only momentum thrust will be present. So you can find out and compare with this. So if convergent divergent nozzle was used, what would have been the momentum thrust, means total specific thrust? Somebody was asking the question, right, in the previous class, that what will happen, means whether pressure thrust is more beneficial or momentum thrust. So you can solve and see. So what we are going to do before going to this turbofan engine, I am going to show you some of the performance characteristics. Okay, by drawing plots, and these codes also I will supply to you. You can also try to run these codes. So in the previous class yesterday, I have shown you one case for this how to calculate the design, how to do the design point calculation for a turbojet engine, and the code also we have seen, and code means not in details, with the output of the code, and we have seen that that matches with the calculation that we have done by hand, means by solving this problem. The same problem was written in the code also. So if we now repeat those calculation for other design parameters, so remember the important design parameters. So there are two important design parameters for any jet engines. One is design means input parameters. One is the compressor pressure ratio, and the second is the turbine inlet temperature. Okay. Apart from this, there are two more parameters. Okay, design parameters, which are the inlet temperature, inlet pressure, means three more parameters: inlet temperature, inlet pressure, and inlet Mach number. Okay, so basically altitude and Mach number. You can see altitude and Mach number, at which altitude at which the flight and the Mach number at cruise velocity. Okay, so we want to see the effect of these two primary parameters, RC and RC means the compressor pressure ratio, and the turbine inlet temperature T03. Okay, let me show the diagram. Let me keep it open. So RC is this ratio, P02 by P01, and the turbine inlet temperature. These two parameters we want to see the effect on the performance characteristics. Performance characteristics is denoted by the thrust or specific thrust and the thrust specific fuel consumption. Less fuel consumption means the engine is better, means better in converting the fuel for generation of certain amount of kinetic energy or thrust. Means if you want to be very specific, less thrust specific fuel consumption means that you need less fuel to generate the same amount of thrust. So it is beneficial to have less value of TSFC. And high specific thrust is beneficial because it means that the size of the engine will be smaller, which is very important because it reduces the weight of all the components and reduces the aircraft weight. Weight is a very important factor for an aircraft. So let us try to look at look at those plots. So how these plots are generated? If you repeat the same design point calculation like we have done previously, but instead of taking a single value, if you take varying value of compressor pressure ratio, for example. Okay, so instead of taking the so in our problem that we had solved in the previous class, the compressor pressure ratio was taken as 8. Okay, and the turbine inlet temperature was taken as 1200, and some cruise speed was taken Mach 0.8, and other variable values were taken. Okay, so altitude was taken as 10,000 meter. So if you keep everything same but vary this compressor pressure ratio, here I have varied from 5 to 30 in steps of 0.1. You can try on your own, like already you have done a similar case. Okay, keeping the turbine inlet temperature T03 same and all the other parameters same. So now for each of these RC, we should be able to get a value of thrust specific fuel consumption and a value of specific thrust, right? For each of these case, we will get a value of specific thrust and thrust specific fuel consumption. We all obviously we have to do the check because now we are varying RC, don't know. So for some cases, the pressure might be greater than critical pressure. Sorry, ambient pressure. The critical pressure might be greater than ambient pressure, means the nozzle may be choked. For some cases, the nozzle may not be choked. So we have to account for both the conditions. Okay, and then for each point, for each design point, for each RC and temperature 1200 Kelvin, we will have 1 data point for thrust specific fuel consumption and one data point for specific thrust. Okay, like for example, again if you go back to the problem in the previous class, for this point corresponding to RC equal to 8 and turbine inlet temperature 1200, we obtain the values as 612 and 0.1278. Okay, 612 and 0.1278. So now if you keep on repeating, instead of 8, if you take RC equal to 9, you will get another value like this. So that we need to plot. So this actually I have written in a more simplified way. I have ignored the fuel mass flow rate of the fuel in this case, and you can include the mass flow rate of the fuel to actually see more accurate calculation. But even if we ignore the mass flow rate of the fuel, the change is very minimal. Okay. So this first figure, I have not put any axis or anything. Okay. This is very roughly actually done. But you will get the trend from here. Okay. So the first figure shows the variation of this is the thrust specific fuel consumption, and this is RC, compressor pressure ratio. Okay, thrust specific fuel consumption TSFC versus RC. Okay, so for our data point of RC equal to 8, thrust specific fuel consumption was 0.127. Okay, this was the more accurate calculation. Here I have ignored the fuel flow value, so it will be slightly different. So 8 will be somewhere around here. Okay, around this value. So it is around 0.11 something we are obtaining. Okay, not exactly 0.12 something, but some error is there. Still you are getting some somewhat correct value. Okay, means almost correct value. And the trend is that if you keep on increasing the compressor pressure ratio, the efficiency of the engine increases. So it keeping the same turbine inlet temperature. Okay, turbine inlet temperature for this graph is 1200 Kelvin. Keeping the same turbine inlet temperature, if you keep on increasing RC value, your specific fuel consumption goes down. Okay, per unit thrust. So it is beneficial to have higher value of RC. Okay, you cannot keep on increasing it to very high value, obviously, because then you won't have much space for this combustion process. The compressor outlet temperature itself will become quite high. But otherwise, the trend is that if you keep on increasing RC, you can go to lower and lower value of TSFC. So generally passenger aircraft which fly for long duration where fuel economy is a very important criteria tries to have very high value of RC. Okay, there are drawbacks of having very high value of RC. Drawbacks are that because compressor pressure ratio is high, you need larger number of compressor stages, and accordingly to run those compressors you will need larger number of turbine stages. So length of the engine will become long, means longer, and weight of the engine will increase. Okay, but still it It is much more beneficial to have low thrust specific fuel consumption, low fuel consumption basically. Any questions? So the second plot is for RC versus specific thrust. Okay, so I will show these plots. These are saved in the video. So if you don't remember what I am saying, it is there in the video. You can go through the video when I will upload it in YouTube. Okay, so the second plot is for specific thrust versus compressor pressure ratio. Okay, same conditions. Turbine inlet temperature is 1200 Kelvin. So specific thrust actually increases up to a certain point and then it keeps on decreasing. Okay, you can correlate this to the effect that it is somewhat similar to the effect that occurs in industrial gas turbines. There is an optimum value. There also we have seen an optimum value where we get maximum thrust. Okay, maximum. There we have seen maximum work output. Here we are getting maximum thrust. Okay, so for example, for this case, it may be around 11 or 12, something like that, where you are getting the maximum thrust. You can again check our values. Again, it will be, this is again based on the approximate solution. Our calculation was based on very accurate solution. So for 8, we had a value of 612. In this case, for 8, you are getting some value around this range. So somewhat higher value you are getting, okay, because of inaccuracy, because we have not considered the mass flow rate of the fuel. Okay, but still you will get of the similar ballpark, means around the same range in trend wheel. If you actually put the fuel air ratio also in the calculation, which can be easily done, then your calculation will be exactly accurate. Okay. So these two plots, actually this figure 2 and figure 1 that I had shown, shows the effect of RC. Okay, figure 2 and figure 1 shows the effect of RC. First one is on thrust specific fuel consumption, so you can say fuel consumption. Second one is on specific thrust. Okay, so based on this you have to decide what type of what should be your, means based on these performance parameters, you initial, when you start the initial design, you decide what should be your initial parameters, like what type of RC you should select. Not only this, for turbine inlet temperature also we have to decide. So remember that these are based on the same turbine inlet temperature, 1200 Kelvin. Okay. So we will also see the effect of turbine inlet temperature. This is specific thrust versus so before going to that, let me just also show the plot of specific thrust versus, means thrust specific fuel consumption versus specific thrust. Okay. So what we have obtained basically this point. So for RC is equal to 5, we know that thrust specific fuel consumption is 0.13 and specific thrust is around 604. Okay, so that is 1 point, 604 and around 0.13. Similarly, the second point is there, third point like this. So towards the end you have RC is equal to 30. At that point you have 0.085 fuel consumption, and this is 588 or something like that. So around 588 and 0.085. Okay. So this plot actually combines these two plots, where the along this line the RC is varying. Along this line the RC is varying, and the y-axis is the fuel consumption and x-axis is the specific thrust. Okay, so this is known as a performance characteristics or performance graph. And if you draw it for multiple temperature, turbine inlet temperature, you will get graphs like this, and it will look something like this. Okay, so this is one case, 1200. Okay, you compare this to our plot. Let me show our plot. Actually, we have the same plot, only the scales are different, so it looks very different. But actually, the plots are similar in nature. Okay, the scale is actually very compressed here. because we are going from 500 to 1000 and our scale is only 580 to 640 because we are drawing only for the same one for one case. Okay, but otherwise if you consider, the nature of the plot is same. Okay, nature of the plot is same. It goes like this for 1200 Kelvin, and same thing we are also getting starting from slightly above 0.12. Okay, so their condition is slightly different. Altitude is 900 meter, 9000 meter, but the characteristic or the qualitatively it is similar. Pattern is similar, and it goes like again because somewhat different, somewhat lower. Okay, like this is happening. So for another, so if you increase, so now from this graph you can see that if we increase the temperature of the inlet to 1400 degree, 1400 Kelvin, you will get a similar plot, but the values will be different. Values will be higher, and corresponding value of specific fuel consumption will also be higher. Okay, so let us also check that case so that we can confirm that okay, we are getting what the book has shown to us. Okay, we are not blindly just reading what is there in the book, but the plots in the book we are also trying to understand properly. Okay. So again, this is on the y-axis we have thrust specific fuel consumption, and on the x-axis now we have uh, turbine inlet temperature. Let me just check what is the RC value here. It is a fixed RC value. So RC is 8 for this case. Okay. So here I have taken a RC of 8, compressor pressure ratio of 8, and for a fixed pressure ratio, we are drawing the variation of uh, specific fuel consumption with respect to turbine inlet temperature. And you can see that just a linear type of plot where the fuel consumption keeps on increasing with increasing uh, turbine inlet temperature. Okay, specific fuel consumption, not the fuel consumption will obviously increase. There is no doubt about it, because if you keep on increasing turbine inlet temperature, your combustion process is much longer because we are keeping the compressor pressure ratio fixed. So the compressor outlet temperature remains fixed, but the turbine inlet temperature increases. So the distance between these 2 points distance between 02 and 03 increases. So overall fuel consumption will keep on increasing, and specific fuel consumption will also increase, because if you draw the cycle for like if you consider that there is unit mass flow rate, because this distance is increasing from 02 to 03, the specific fuel consumption also increases. Okay, but the important point is that not only that, the thrust specific fuel consumption is increasing, means the rate at which the specific fuel consumption is increasing is higher than the rate at which the thrust is increasing. Okay, so like this. So where was our plot? This one. Okay. Similarly, if we take a look at the thrust should also increase. Okay, thrust should also increase with the turbine inlet temperature. Again, going from 1000 to 1800 Kelvin. So thrust is increasing from say 500 something to 800 something. It is linearly, almost linearly increasing. Our case was around 1200 Kelvin. So it was around 600 something. Okay, 610 or 12 was our exact value. You can see that we are almost getting similar value, almost getting the correct value. Okay, for this case. So if you combine these two, then you can generate this type of plot. Okay. So now you can, if you assume that the RC is constant, for example, our case, the plots that I have shown, RC was 8. Same thing you can do for RC equal to 10. Okay. I can do the same thing for RC equal to 10. If you draw for RC equal to 10, this is the, and then combine those two plots, specific fuel consumption and specific thrust, you will get a line like this, because both are increasing with turbine inlet temperature. SFC versus specific thrust also will look like this. Okay, similarly for RC equal to 5 you can draw, RC equal to 8 you can draw. So all these lines you will get. Okay, And on the other hand, by keeping the turbine inlet temperature constant, if you vary RC and draw specific fuel consumption versus specific thrust, you will get lines like this. Okay, I have already shown you. So if you combine this, you get this performance map. This is known as the performance map. And here it is a very crude map, but this type of very elaborate maps can be generated by doing lot of calculations, and can be used like a handbook or like a reference by the actual engineers. Means where there will be much more data points like 5, 5.1, 5.2 like this, like a steam table. You can not steam table means like a Molière chart, or like a chart will be there 5, 5.1, 5.2 like this, going on to high values, and then more data points will be there 500, 510, 520, and you can actually find out at what condition your desired thrust or desired fuel so say you are starting a design and you decide that I want this amount of specific thrust and this amount of fuel consumption. So you can locate what should be your turbine inlet temperature and what should be your RC value. Means preliminary RC value and preliminary turbine inlet temperature. So say I want a design where I need very low fuel consumption, 0.12, and very high thrust, 800 Kelvin. 800 Newton per kg per second. Okay, sorry. So I will draw a line like this and draw another line like this, and we see that we need approximately compressor pressure ratio of 15 and turbine inlet temperature of say 1550 or 1560 Kelvin. Okay. So based on that, we will start with the preliminary design, and then we will move. Once we do the design, then we will back calculate exactly what we are getting. So what is the actual thrust we are getting for different Mach number, things like that. Okay. So this is only for the typical Mach number. So if you change the Mach number or altitude, again the performance map will change. Okay. So how this will change, I can just give you a brief hint. Okay. So if you vary the Mach number, if you increase the Mach number, typically what will happen is that uh, the specific thrust uh, actually will decrease. If you increase the Mach number, specific thrust will decrease. If you increase the Mach number, the inlet velocity increases, and it causes a momentum drag. You remember what is the momentum drag? This m dot v minus vi was there for calculation of thrust, right? So the negative term minus vi term, that increases, and as a result, it actually influences the specific thrust. The specific thrust goes down, and the specific fuel consumption increases at higher Mach number. Okay, more momentum drag is there, and also another point is there that if the Mach number is higher, your after the diffusion process. So if you go to the diffusion process, please remember these points, or they are there in the video also. They are not there in the notes. Okay. So if you have higher Mach number at the inlet, what will happen to this 0.01? Where will it be located? Will it be higher or lower?
Higher.
It will be higher, correct. So it will be higher, and if you have a fixed compressor pressure ratio, same pressure ratio, say 8, this 0.02 will also, because 02 by 01, T02, P02 by P01 is fixed, right? So the compressor will occur, compression process will occur at a higher temperature. And if keeping the pressure ratio same, if compression or expansion occurs at higher temperature, what is the change in enthalpy that occurs? Is it higher or lower? For the same pressure ratio, if the for an expansion or compression process like turbine or compressor, for same pressure ratio, will the change of enthalpy be higher at higher temperature or at lower temperature? We have discussed this multiple times in the beginning of the course.
Like higher at higher temperature.
Higher at higher temperature, because the constant pressure lines are diverging, right? These constant pressure lines are diverging. So because they are diverging for the same two constant pressure lines, if you consider the, say, where there is no pressure loss. So for the same, this also does not have that plot. Anyway, for the same pressure ratio, the if you keep on increasing the temperature, so if I go towards the right hand side, the gap between the constant pressure lines in the TS diagram keeps on increasing. Correct? We have discussed this many times in industrial gas turbines. That is why you use intercooler and reheating, all these things. So if you can shift the process towards the left side, the work output is reduced. If you shift the process towards the right side, not work output, sorry, work input is reduced. If the process gets shifted towards the right side, work input increases. So if you go to higher temperatures, okay, if you go to higher temperatures, the compressor work input actually increases, and that actually leads to higher fuel consumption, means for generating the same thrust, higher specific fuel consumption and lower specific thrust, because more work is required for the compressor. That also plays a role apart from the momentum drag, inlet drag. Okay, and the opposite effect is seen if you increase the altitude. If you go to higher and higher altitude, okay, at higher altitude the inlet temperature is lower, and inlet temperature plays a very important role. Okay, so inlet temperature is lower. So if the inlet temperature is lower, your compressor ratio, okay, and for the same Mach number, and same pressure ratio, compressor work input will be, and as a result, you will get uh, the opposite effect. Basically, you will get lower specific fuel consumption, means fuel consumption will be lower, and higher specific thrust. This is only considering the engine. There are other benefits also at higher altitude, like the drag is also less at higher altitude because of the thinner air, but the lift is also less. That is a drawback, but the drag is less. Okay, but those are external conditions. Internally to the engine, the fuel consumption is improved, means you need less fuel consumption. Okay, because less compressor work input is required. Remember, it is very easy to remember what I was asking, that what will happen if the temperature is changed to the change in enthalpy. Okay, if the change in enthalpy was not affected, okay, with temperature, if this constant pressure lines would have been parallel, so we would not have been able to generate any work output, means any net work output, because the work input to the compressor would have been equal to the work output from the turbine in an industrial gas turbine. Okay, for the same, so industrial gas turbines operates with same pressure ratio, right? Turbines and compressors both have same pressure ratio because there is no nozzle. So if the pressure ratio is same, the only reason why you are getting more work, some net work output from the cycle, is that for the same pressure ratio, turbine is generating more work, means the enthalpy change in turbine is more as compared to the enthalpy change in the compressor. Okay, and that only occurs because the constant pressure lines are diverging, and as a result, you get for the same pressure ratio, because the turbine is operating at higher temperature, you get higher work output as compared to the work input required in the compressor. Okay, otherwise it should not have been possible. Idea? Any questions on this? Okay, I will finish this part with this discussion. These are from the book of Cohen. Okay, so if you want, you can go and check there also. But we have also tried to, I have tried to relate as much as possible to our actual calculations instead of just blankly going through this plot. Like I wanted to show how we can also draw this plot using MATLAB, so that you get a feel of the actual performance characteristic, how they are evolving. So this is the same thing. Okay, this is the same plot. Here they have put it in a more general way. Okay, instead of putting values. So this axis, it shows increasing turbine inlet temperature. Okay, along this line, similar to this plot. In a more general way, they have shown turbine inlet temperature is increasing, and these are the lines corresponding to increasing pressure ratio. Okay, so they have written pressure ratio is increasing. Okay, and this side you have the specific fuel consumption, and this side is increasing specific thrust. The same plot, but in a more generic way. Okay. So what is the reason of showing this? The reason of showing this is what type of engines, what type of design is required. Okay. So for example, they have shown three cases. One is say long range subsonic aircraft. Okay, long range subsonic aircraft are what type of aircraft? The normal passenger aircraft that we use every day. Okay, or for general flying. So from say here to Delhi or even to longer distance like from here to London or some place like this. Okay, so which will have a long cruise distance. So in those cases for passenger aircraft, the most important, what is the most important consideration? Fuel economy. Running an airline company goes towards the cost. Okay. All the extra things are means lower component of cost. Okay. Almost half the cost goes towards fuel, and all the other things like all salary, everything, maintenance, everything else is secondary. So fuel cost is very important, and you want the engines to be as fuel efficient as possible. Okay. So you need the maximum specific thrust and minimum thrust specific fuel consumption that is possible. Okay, maximum. So first point is that minimum fuel consumption is required, minimum specific fuel consumption, so that you get means you can fly at low cost, fly your aircraft at low cost, and maximum thrust you want, maximum specific thrust, so that the engine size is lower, which will reduce the weight and drag also. So mainly it will reduce the weight. Okay, weight is also very important parameter. So you operate somewhere along this point. Okay, so where the thrust is also okay maximum as much as possible, and fuel consumption for that maximum thrust fuel consumption is as minimum as possible. Okay, so for this region, what is the main drawback? Means let us before going in, try to understand what will be the design changes that will happen. Okay, so if you keep on increasing the pressure ratio, what will happen is that what will happen to the number of stages of turbine and compressor for increasing pressure ratio?
Increase.
It will increase. Okay. So if you keep on increasing the pressure ratio and the number of compressor and turbine stages keep on increasing, so what happens? How does this look like? I have shown you that how a typical gas turbine looks like, right? So what will be the size of the blades for the first stage as compared to the last stage in a compressor? First stage blades will be longer or shorter?
Longer.
Longer.
It
And
will
the last stage blades will,
smaller.
gradually the blade length will shorten, right? Why this will happen?
Specific volume.
Specific volume will decrease.
Decrease.
Density will increase because of high pressure. Compressor is increasing the pressure, and because of high pressure, pressure increases at a higher rate as compared to temperature. So the pressure has the most effect on the density. Density will increase. Okay, and because the mass flow rate is constant, your annular area through which the gas is flowing has to decrease. Okay, so the length of blades keep on decreasing. So if you have a single shaft and very large number of stages mounted on a single shaft, what is the problem? Say I have 15 stages of compressor, 15 compressor stages. Each of this is a stage mounted on the same shaft. Can you foresee some problem? Some problem is there.
Sir, unbalancing of the ground.
Not really,
Like
because
inertia will increase.
weight can be managed. What will increase?
Inertia.
Inertia will increase, but not a very major. It does not play a very major role. It's just towards the start. Okay, once you are have started rotating, and these are gas turbines actually start very fast, not like steam turbines. So that does not play. What about the stresses that are generated in the blades? Always think about, whenever I ask any of these questions, first consideration is the blades, because blades are the most costliest part of a gas turbine. Okay, blade materials are particularly for turbines. Okay, not for compressor, but for turbines, what will happen if you keep on increasing the number of stages? The first stage will have very small blades. The last stages will have very large blades. Okay, so both for compressor and turbine, similar thing is happening. So what happens to the stresses that are generated?
Like they are high for those long blades.
They will be much higher because the rotational speed is same. So if rotational speed is same, but the tip velocity keeps on increasing, okay, means the diameter keeps on increasing, you will get higher stresses, higher centrifugal stresses. Okay, so it is then you need better and better materials or more costly materials, or some like need to have thicker blades. Means somewhere the cost is going to increase. So at some point it is not beneficial to have a single shaft, but you have two concentric shafts, means one inside the other, and the shaft that is on the outside, okay, the shaft that is, say you have a shaft on the outside that runs the high pressure compressor stages and the high pressure turbine stages, and there is another shaft which goes through the inside which runs the low pressure turbine stages and the low pressure compressor stages. Okay. What is the reason for this? I have not yet stated the reason. So there are two shafts, concentric shafts. The one of the shaft is running the high pressure compressor stages and high pressure turbine stages, and the other shaft is running the low pressure compressor stages and the low pressure turbine stages. What is the benefit of using these two shafts? Quick answers are needed. Every day we run out of time. So
Stresses can be like both the shafts handle different stresses.
yes, both the shaft
Handle different stresses, right? Because both have different type of blades. One will have longer blades, one will have small blades.
no, but if it is then why not a single? Why not a single
So
shaft?
to reduce
What's the?
centrifugal stress.
It will reduce centrifugal stress. It will reduce, but how it will reduce? And for what? Which stage? Why it will reduce?
Speed up to turbines are different.
Speed of two turbines has to be different. So the shaft has to rotate at two different speeds. Okay, which shaft will rotate faster? Which shaft will rotate slower?
Sir, high pressure turbine blades
High pressure, sir.
actually rotate faster.
High pressure turbine blades will rotate faster, correct. And the low pressure stages will rotate slower. Okay, because the blades are longer for the low pressure stages, they have to rotate slower. So by having two shafts, you can actually have different rotational speeds, and which is more means better in that sense. Okay, uh, you can handle the stresses. So this type of turbines are known as two spool turbines. Okay, the turbines that spool turbine, and these are known as two spool turbines. And if you keep on increasing the pressure ratio, you have to go from single spool to spool turbines. Okay, so that is a major design change that will occur if you keep on increasing the pressure ratio. Network quality poor. Can you hear me?
Yes, sir.
Okay. The other design aspect is that if you keep on increasing the turbine inlet temperature, at higher temperature you will need very sophisticated cooling mechanisms like cooled blades with ceramic coating and things like that, internal cooling of the blades. But if you have lower turbine inlet temperature, as to very low temperatures, you don't need sophisticated cooling mechanism. You can use general normal uncooled blades also. With cooling passages can be used, but if you keep on increasing the turbine inlet temperature, the cooling becomes more and more complex. Okay. Again, bad network. Again, can you hear me?
Yes, sir.
Okay. See, bad network means that sometimes the connection goes off. So this why I am telling all these things, these different types of two spool, one spool, uncooled bed, cool bed, because once you look at the performance map and you have decided that we want to develop a passenger aircraft. Say Boeing has decided that we want to develop a new passenger aircraft for long distances. Then the most important criteria for them is that low fuel consumption and high specific thrust. So they will look at some region in the aircraft in the design map, performance map like this, and based on that they can decide that okay, for this we will need multi-spool and also sophisticated turbine cooling is needed for our cases. Okay, but that will lead to more cost, initial cost. So the aircraft cost will be higher. For multi-spool design is more complicated. Then for blade cooling design is more complicated. Blade material has to improve. Okay, that is not shown here. But as you keep on going towards this side, blade material has to improve. You have to go to single crystals and then better and better super alloys. Blade material has to improve. So the initial cost will be higher as you go towards this side, towards this corner. Initial cost of the aircraft will be higher. Cost of development and cost of manufacturing will be higher. But the long-term cost will be lower. Operating cost will be lower. Okay. And that is the important criteria for this passenger aircraft. On the other hand, if you consider a business jet, okay, business jets are also have jet engines, but are very small size, smaller in length, and they do not fly as regularly as passenger aircraft. So a typical passenger aircraft, say you take this, consider this Indigo, okay. So they will start from morning 5 o'clock, one single aircraft. Say this aircraft starts from New Delhi. So it goes from New Delhi to Mumbai, from Mumbai to New Delhi, again New Delhi to Kolkata, Kolkata to New Delhi, New Delhi to Bangalore, Bangalore to New Delhi. It keeps on flying, means it does not stop after one flight. It will keep on flying until the late night flight. So until say night 2 o'clock. And then there will be 2-3 hours for maintenance. Again, next morning it will again start flying. The aircrafts are extensively used. Okay, continuously they are being used. It is not for a single flight per day. So around say 7, 8, 10 flights per day will be there. For long distance aircrafts also they will be continuously used, almost continuously used except for the maintenance period. So that's why this fuel consumption was important. Business jets on the other hand are personally owned by different businesses like companies or even very rich person, and they will fly much less frequently. Okay, they will fly much less frequently as compared to passenger aircrafts. So in those cases, the cost becomes the important criteria. If you want to purchase a aircraft, like if you are a rich person, very rich person, okay, like Shah Rukh Khan, if you want to purchase a business aircraft for yourself. So in that case, you will try to look at what is the price of the aircraft, initial price of the aircraft, like we look at the initial price of a car or a bike. Okay, and because it will not be so frequently flying, so although it is important fuel consumption and thrust, but it is much less important as compared to passenger aircraft. Okay, so we can locate a design which is in this region. Okay, higher fuel consumption may be allowable and lower specific thrust may be allowable. Okay, but what it will do, you can go towards less sophisticated blades with less costly materials and less complicated design, single spool design. Okay, so initial aircraft cost will be much lower for these business jets. There are other types of aircraft. So one particular type they have shown in this are actually where you need to lift very heavy duty material, okay, for very short duration. So during this lifting period, very high thrust is needed. These are for military aircrafts. Very high thrust is needed during this lifting. Okay, but you are not bothered with fuel consumption. because they operate for short distances and because they are military aircraft, fuel consumption is not the most important criteria, but very high thrust is required. Okay, so in those cases, you can go towards this side or even this side. It's not there, but even this side where fuel consumption is not important, but thrust should be as high as possible. And yes, I cannot hear you. Somebody was saying something. Any question? No. Okay. So again, based on that, we have to decide what type of things will be there. So single spool is sufficient. You can use single spool, but cooled blades will be needed because turbine inlet temperature needs to be high to generate higher thrust. Okay. So this is the role of performance characteristics or performance maps. For other aircraft, we will not go into this kind of details. Only for the turbojet, I am showing to just build on like to so that you understand that everything is related. All these calculations we are doing are not in vain or not very academic. They are actually practical. The calculations we have done, the problem that I had given is actually a very practical problem and actually plays a role in designing the aircraft. Okay, it's not a like just develop like I have developed some academic problem just to create some exercises so that you can get some marks, solve and get some marks. All these have actual design applications. Okay, all of them are related together. This performance map and these actual designs. We'll stop here. Next class we'll start the turbofan engine. Okay, I will have another extra class next Monday from 6 to 8. Most probably all Mondays it will happen. Okay, the situation has become that all Mondays I will need extra classes from 6 to 8. Even more extra classes may be required. We will see towards the end. So let me quickly take the attendance for today. Read from the and try to solve go through the solve problem, means try to solve on your own the problems that I have told today, 1, 3, 5 and 6. All of them are very long problems. It will take some time for you to solve and then try to see the answer. Don't just go through the answers directly, then you will not understand the nuances of the problem. Any questions on this turbojet part, what we have discussed for the last few classes? On nozzles and diffusers also should be clear because we will not repeat this discussion. If you want, you can go to the recording. Please switch off your mic. I am getting some feedback. Okay. So 12. Bharatram. Bharatram, where is Bharatram? Cannot see name. Bharat is absent. Sachin, I can see. Sachin is present.
Yes,
Sanjay
sir.
is present. Abhishek is present. Vikas is present. Manthan is present. Ajay Kumar Meena. Ajay. I cannot see Ajay Kumar Meena. Is it here somewhere? Gaurav is present. Then Jishnu Shankar Barua is present. Suresh Kumar present. Ujwal is there. Ujwal is present. Shubham Kumar is present. Pushpendu Das is present. Shyam Kumar is present. Prabhat Kumar Mishra is present. Kishan Sai, Alapati Kishan Sai present. Then Venkata Rajendra present. Atul Jyotish present. Ramcharan present. Suman is then Ashwini Kumar. Ashwini Kumar is where is Ashwini Kumar? Ashwini Kumar. Ashwini I cannot see. Ashwini is absent. Then Gaurav Srivastav present. Gulshan Kumar present. Pujari. Where is Pujari? Pujari is present. Nilesh Kumar. Chintu Sai present. Sudipto Das present. Lokesh Sonkar. Lokesh is present. Then Ankit is not there obviously, and then
Sir,
Shivansh
Lokesh present,
Das
sir.
is present. Yes, not present. Shivansh is also present. Absent is Bharat Ram. Bharat Ram is absent. Ajay Kumar Meena and Ashwini Kumar. Apart from the two students who has left. Okay. We will meet on Monday. I will again send a reminder email. Monday 6 p.m. We are lagging a lot. Go through the solved problems also. Okay. I will send you after finishing the turbofan. I will send you problems. Thank you.
Thank you, sir.